This talk is titled Programs as Singularities. I'd like to begin by saying thank you. It's awesome to be here. It's awesome to present this work. I've worked out that Iliad 2 is a place where if you ask for things, you get them. I asked if I could do the talk inside Rat Park, and here we are. Tons of people interested, which is totally awesome. I also asked if I could get my hands on the drum kit here, and I managed to pull through on that as well. More on that later. So who am I? My name is Will. I've done my PhD in algebraic geometry and linear logic. So that was completed in 2024. And then since then, I've done a postdoc at the University of Melbourne, hired by Daniel Murphy. And the main output of that postdoc was the Programs as Singularities paper, which has been submitted, and that's the content of today's talk. Currently, I'm a part-time employee at Timaeus. I love having philosophical or even practical conversations about existential threat as much as the next guy. But in my soul, I'm a math nerd. So my main approach to AI safety and all the other things that we've been talking about in this conference so far has been the beautiful mathematics that I have been lucky to study behind SLT. I'm also a part-time musician and performance artist. I only mention this because there is a huge range of people that are very interesting at this conference, and I think that sometimes it's helpful to wave a few flags. I am working on projects outside of my work in Timaeus. So I've got various mathematical musicology projects. I'm working with a master's in music student on various different things. This is stuff not relevant to the talk, but if anybody has interest in these types of things, please do talk to me about it. And as far as the performance stuff goes, I've done these fun little mathematics drumming performances. That's what you see on the left there. And on the right, that was a collaboration that I did with some of the world's best GoldenEye 007 speedrunners. That was a lot of fun. All right, so let's get to talking about mathematics. Algorithmic structure and geometric structure, or structural Bayesianism, as this talk has been pitched several times. So we could be interested in expanding the proper domain of logic or computation to include that which emerges inside large language machines other than ourselves. And one way of doing this is to embed proofs or programs viewed in the same light via the Curry-Howard correspondence into machine learning or singular learning theory. If we were to create such an embedding, then this embedding really should be a homomorphism. I'm using the phrase homomorphism here somewhat as an analogy. What I really mean is that it should be structure preserving. So what we want to do is look at something that is computational and has algorithmic structure, which we can look at and observe, and then embed that into some kind of geometric setting where we can see reflections of that algorithmic structure inside the geometric structure. Okay? And today's talk is basically just an example of one of these homomorphisms, somewhat of a proof of concept. And indeed, it's the main takeaway from the paper with the same title as the talk. On the right, you can see some examples of the geometry that you get when you analyze the algorithmic structure geometrically according to the tools that I'm about to present for you. And these pictures are totally awesome. There's a lot that you can say about them. The picture credit is to Billy Snickers. He's talking next, and he'll be running through some of those diagrams by way of example. Very cool stuff. Why believe in this in the first place? So I've stolen this motivation from a talk that Dan gave a little bit earlier. It's worth saying out loud that all of the work I'm talking about today has been done in collaboration with Daniel Murphy. Okay, so there's this quote. If you're a scientist or if you're an engineer and you're trying to understand effective causality, then you really want to understand the perturbations of every constituent component of that thing that you're trying to study. That's somewhat wrapped up inside this quote. And the simple question that we began with is, what would it mean to perturb the computational process of a Turing machine? What would that mean? A very natural first suggestion would be to instigate probability somehow. So if I were to perturb a Turing machine, maybe that means to put some kind of probability into its inputs. This can be done using standard propagation of uncertainty through a Turing machine. However, we believe that this is insufficient, as you end up studying the probabilistic extension of the function which is induced by the Turing machine. And that's really not what we mean by propagating error or uncertainty through a Turing machine. We really want the error or the uncertainty to be propagated through the computational process itself. So what would that mean? The way that we thought about this was by running simulations of Turing machines on a fixed choice of universal Turing machine, and then considering perturbations of that computational process. So we fixed a very particular universal Turing machine. It's a so-called staged pseudo-universal Turing machine. And this is really important to a lot of the work that Dan and I have done in this paper, and also to the examples that Billy is going to talk about inside the next talk. So I'm going to spend a little bit of time right now explaining the actual computational process of this particular universal Turing machine that we take. First and foremost, we work with a fixed alphabet and set of states. So sigma is just some size n set, and q is some size m set, where sigma is the tape alphabet and q is the set of states of the Turing machines that we're trying to simulate on this universal Turing machine. Now, what this means is that a Turing machine is completely determined by its transition function, which can now just be given as a sequence like this. So when you see sigma 1 prime, q1 prime, d1, that corresponds to the first output that you get from the transition function of a Turing machine that you're trying to simulate. So when you see sequences like these, I want you to be thinking about them as the code for a Turing machine, which is going to be taken by this universal Turing machine. The universal Turing machine has got 4 tapes on it: a description tape, a staging tape, a state tape, and a working tape. The description tape is where the code for the Turing machine that you're simulating goes. Okay? So that sequence that I've got up here with the green arrows pointing to it just goes straight onto the description tape. The staging tape just only makes use of 3 squares, and it's just got X's on it to begin with. I'm going to come back to the staging tape. The state tape only uses a single square, and it just stores the information of the state of the Turing machine that we're simulating. And then down on the bottom is the working tape. This is how the universal Turing machine simulates the actual computational process on the tape of the machine that we're simulating. Okay, so what is the actual operation of this universal Turing machine? Well, initially all of the heads are on the far left, except for the staging tape, which is in the middle, but don't worry about that for now. Pay attention to the description tape. If the head of that tape is right on the left, then it means that we're looking at the first output of the first symbol inside the transition function of the Turing machine that we're simulating. And then we're going to compare that symbol to the symbol that is underneath the head of the working tape. And that's in order to see whether we get a match or not, to know in the next step if we should then compare the state, and then if we find a match, then we're going to write down the correct output of the transition function onto the staging tape as we continue moving along the description tape. Okay? So to summarize, the Turing machine is going to go along the description tape and just search until it finds a match. And when it does, it just puts that information into the staging tape to then update the working tape at the next phase of the computation of the universal Turing machine. Okay, so after the first pass, the staging tape is ideally occupied because the updated symbol, the updated state, and the updated direction have been written onto it. And then there are a few and a fixed number of steps that are dedicated to updating the state and the working tape. And then the description tape simply moves the head back to the very start, and we clear the staging tape back to the X's, and then we're ready to simulate the next step of this Turing machine. Okay. Any questions about that? Good. So this naturally gives us a space of Turing machine codes. It's this space W code, and it's just the product over all sigma and q, where lowercase sigma is ranging over capital sigma, our alphabet tape, sorry, our alphabet language, our tape alphabet, there we go, and q is ranging over all of the states. Okay, so an element of this space is just one of those sequences which I'm using to describe the code of Turing machines. And then what we want to do is fix one of the squares on the description tape of the universal Turing machine and then consider a perturbation of that square. So what do I mean by a perturbation? Well, at this point, we introduce the probability simplex. So just as an arbitrary definition, if Z is a set, then you can define delta Z to be the functions from Z into the closed interval from 0 to 1, such that these entries sum to 1. This is just probability distributions over the set Z. The reason why I introduce this is so that we can define a concept of a noisy Turing machine, which is given by a function of this form, which is very similar to the form of a regular Turing machine, but now our outputs are able to be distributions over the alphabet states and also the directions. Okay, and you can see how W code naturally embeds inside this space W. And one point of remark about the space W is that it is a smooth manifold with corners, right? So now that we have a smooth space, we would hope to install it with non-trivial topology, which will allow us to study the local neighborhoods of elements inside W code.
Question?
Yeah.
So just to review naively,
Yeah.
sigma and q are properties of the universal Turing machine. They're not separate for each Turing machine you're encoding.
You're talking about lowercase sigma and q, or
Uppercase sigma.
yeah. So it's somewhat a property of the universal Turing machine. It's the choice of alphabet and the choice of states which our universal Turing machine are able to simulate machines that use that alphabet instead of states for. So to put it simply, fix a set sigma, which is your alphabet, and then fix a set of states, q, and then we're going to consider a universal Turing machine which is able to simulate Turing machines with that alphabet and set of states.
Don't Turing machines have to be arbitrarily big and you fix them?
Yep, absolutely. So in that sense, this is not a universal Turing machine. Okay. It's a staged pseudo-universal Turing machine. We're also going to only run it for a fixed number of steps, blah, blah, blah. Was there another question?
Maybe intuitively, the program stays the same, but the compiler is noisy, or they...
Interesting. If we're talking about the program as being the code that we put onto the Turing machine, it's not really the same. I mean, we are actually going to change one of the symbols to a probability distribution over that symbol, right? Indeed, this is fuzzy or noisy computation, or, you know, however you want to think about it. But it can make a difference. That's kind of the point. You want to look at all of the local perturbations and see what makes a difference and what doesn't. And then we want to describe those differences geometrically. Make sense? Yeah. Yeah.
So, I guess as long as, so there's going to be a continuum of elements in the simplex, but I guess there will be some dense subset that are computable real numbers, and then you could always have some probabilistic Turing machine that simulates this behavior, right? But you have to add some more states and the stream of random bits, and then, right? So ultimately, so you're basically expanding this from the space of deterministic Turing machines into some built-in set of probabilistic Turing machines.
Yeah, 100% we are taking our set of Turing machines, which is some discrete set, and then we're going to embed it into a continuous space. It sounded to me like the first part of your question was asking about computability of those probability distributions, in case I take some...
Well, I guess I'm just saying that there will be some dense set within this larger space that are the computable probability distributions. Right? So in a way, this is like you're just spending to a set of Turing machines, probabilistic Turing machines, and kind of fill it, taking the closure.
Sure. Okay, yeah, we can think about it like that. We are taking a very particular type of probabilistic Turing machine, which is a non-standard one, and that's an important part of the theory. I'll talk about that as well. We didn't think about computable probability distributions. Did you want to say something, Dan? Or?
I think that's not quite correct. It's the way we're going to execute those other points, not going to...
That's okay, that's what I'm curious about. What's the difference?
It's not dense. It's not that there's like a set of dense, computable, like this. You're interpolating sort of between, you have some a hybrid people interpolating the deterministic programs that are pointing to this hybrid people, rather than what you're suggesting that there's like a dense set of computable.
What he was saying makes sense, but the answer to your question is
Okay, sure. We can talk about this after.
Cool. So maybe this is actually going to clarify things. Computing with perturbations, what does it look like? So I think I've made the point, but I just really wanted this image to kind of be in mind. These are the 4 tapes of the pseudo-universal Turing machine. And the top one is the description tape. So you've got zeros, ones, describing your Turing machine. And then we're going to fix one of the squares and introduce a perturbation. So where you see 1 minus epsilon 0 plus epsilon 1, think about that as the correct symbol there is a 0 with a small probability of having a read error where you read a 1 instead. But you sample from that distribution. That's why I've put this 1 here. It's not as though the entire distribution flows through the computation of the pseudo-UTM. Instead, we sample and then move whatever we get. So say we did make an error and have that 1. We move that into the staging tape, which then gets propagated all the way through the computation. Okay? Cool. So since we're not just taking standard probabilistic Turing machines, we want it to be principled in the way that we construct the propagation of error through our universal Turing machine. And the way that we did that was we made use of linear logic. To this particular audience, it's probably worth saying out loud, you don't need to know linear logic to understand our paper, okay? And it was important to us that we wrote it in such a way that hopefully that was transparent. I'm not sure if we succeeded. But you don't need linear logic in order to understand it. But it was a language that we used in order to construct the precise way in which probability, the precise way in which error flows through the computational process. And then we distilled all of the linear logic out at a certain point. You can just think about it as a particular probabilistic Turing machine, but you need to kind of just accept it on the nose if you don't take the background of linear logic into account. So this is the only slide where I'm going to talk about linear logic. What is it? It's a formal language. It's a system of logic. And nowadays, computer scientists are familiar with the Curry-Howard correspondence, which allows us to view certain constructive logics as systems of computation. Linear logic is no exception. And linear logic is cool because it comes with a natural notion of derivative. Yes, I'm telling you that you can take the derivative of your algorithms, which is not so surprising nowadays, but when I was 10 years younger and I was meeting Dan for the first time, that was super cool for me. So, to achieve the smooth relaxation of the computation of a Turing machine, we actually encoded Turing machines running for a fixed number of time steps t into linear logic. And then we looked at the naturally occurring naive probabilistic extensions of the algorithms inside linear logic, the way that those things perform on the proofs encoding Turing machine specifically. So as I said, linear logic has a natural notion of derivative inside its syntax. And so this also allows us to analyze the derivatives of the proofs, in particular, the proofs encoding the computation of the staged pseudo-universal Turing machine. And we claim these derivatives are interesting. So instead, what you should think about is this. Now, I apologize for putting this slide on the screen. But you know what? I don't apologize. I'm proud of myself for putting this slide on the screen. I wanted to explain it, and I wanted to have some chance of the people at the back being able to see it. So, you know, no title, no words. What are we looking at? Okay, this is the way that error propagates through our staged pseudo-universal Turing machine, just concretely written down as a graphical model. So every single node here is a random variable, and all of the arrows give you the dependencies on those random variables on what precedes it. To help you with reading this diagram, it mostly goes from 0 up. There are some diagonals, but you never go down or sideways or anything like that. Over on the far right, you'll see this counter from 0 up to 10n plus 6. Capital N here is the number of blocks of 5 here. So what's n? N here is determined by how many symbols and states you have inside your inside the machine that you're simulating. Okay, but these time steps are just the true time steps of the universal Turing machine, and 10n plus 6 such steps gives you one simulated step of the Turing machine. Okay, so we're looking at a single step of the Turing machine that we're simulating. Is this symbol visible? There's a theta here. Okay, that theta is where we're introducing the error. So this is the 1 minus epsilon 0 plus epsilon 1 that we saw on one of the previous slides. And then what you want to think about is everything that precedes this theta. So everything for which there is a directed path from theta to that random variable has a dependency on that error that you introduce. Okay? So this gives us a way of thinking about the probabilistic computation of the UTM. And yeah, when Dan, myself, Billy, etc., thinking about these computations, this is truly the diagram that we have inside our heads. Okay? Yeah, question.
Okay, so now I guess maybe am I prepared to ask the question? So if theta is a computable number,
Yeah.
then it seems to me that I could introduce some more states where I run a computation of theta and I flip a bunch of coins, right? And I get more and more precise intervals for theta. And once I know that my coin flips kind of land, I sample from the uniform distribution. If my coin flips land below theta, right? Then I take the transition, the one transition. If they land above theta, then I take the other transition. So I end up writing something on a different thing on my tape, depending on what I take a different transition depending on what I see. Right, so I still don't understand how this is not. I mean, at least for the computable perturbations, I still don't understand how this is not.
Dan, do you want to grab this?
So the question was, like, why isn't this just executing a probabilistic Turing machine? So the reason is, if you think about the model of the UTM executing this code, it's quite exotic in the following way, where every time it's going to read from a square at some later step, it's going to sample as many times from that original uncertainty as it needs to in order to reconstruct every step in the chain leading to that square. So it's like some wildly growing number of samples where you sample like many, many, many times all the way back to the very beginning, which is, so you could probably simulate that as a probabilistic Turing machine in some way, but this is not the usual way. So I'm not disagreeing that like you could not reach the same output probability. I'm not saying it's uncomputable or something, but it's not the usual way you would parameterize a probabilistic Turing machine, in my understanding.
Yeah, I guess, okay, I think that's a little bit, but
Yeah.
I'm still not sure I see how it's different. Because at the end of
It
the
seems
day,
like it
when
has
you get to the
different memory
output,
constraints.
what?
It seems like it has different memory growth profile as it runs.
So I'm not sure it does. Like when you get to the final output, then you just propagate all the way back.
I think that might be true, but it's sort of, okay, so what?
So this then, well, I mean, it's not so much a. I mean, I'm just saying, is this?
Yeah, so the claim is not this is some exotic, interesting new class of computation. The claim is that this is a way of constructing a geometry which is interesting. So if you do it that's maybe an also like a related or maybe the same way of coming across the same geometry. So the claim is not that this is like something that's completely outside of like probabilistic Turing machines. Yeah.
There's another question here. Did you?
Well, you can answer the questions.
Thanks. Zap. Oh, yeah.
Oh, yeah, I just had, so, like, would it be a decent summary to say that sort of probabilistic model here is you sort of flip, a bit of your, like, source code, basically, or the, the machine description at random, and then you keep it flipped until it flips back, basically, for the rest of the computation?
I wouldn't say so. You're replacing a bit in the description tape with a distribution.
Yeah.
And then every single step of the universal Turing machine thereafter that at any point in its history can be traced back to that distribution, you're going to resample. So you definitely don't like fix it. And this is important. You don't take one sample once and for all, or even for one simulated step and then do it again. It's really not like that. So if you're really deep inside your computation of your pseudo UTM, there's just going to be a ton of dependencies back on that square from ages ago. And that's what happens.
Okay, you resample every random node in your like past history.
Yeah, so every time you come...
I see. Yeah.
I saw another hand, yeah.
So equivalently, could you just kind of represent every dependent node itself as a distribution rather than actually sampling it and kind of stay in distribution space? Do you ever have to draw samples?
Yeah, you can do that for sure. So the question is, do you actually need to do the resampling, or can you just basically consider the distribution induced on all of these random variables? Which certainly you can. And you come into...
I'm just going to sit in the shade somewhere. I don't have anything there.
The reason why we do this is because we want to think about this as an ongoing computation, right? But so on the next slide, I'm going to talk about this function, which takes in an element of, say, some kind of, some string, and then a noisy Turing machine, which is one of these codes in W. And then it outputs the distribution on the state at the very end. This is just a simplifying assumption to say, okay, this is crazy. What if we just fix one of these states and then look at all of its dependencies after, say, 2 simulated time steps?
I think, Will, you didn't describe what the columns are. Maybe
Oh, that's a very good point. So each column is, each group of columns is corresponding to one of the tapes on the pseudo-universal Turing machine. So this first column, which has a lot of blank entries on it, is the description tape, okay? I haven't put in every single symbol because it's deterministic and you don't need to. But this theta being the thing that we're considering as a perturbation, that's happening on one of the squares on the description tape, okay? So this column corresponds to the description tape. The next 3 columns correspond to the staging tape. The next 2h plus 1 columns, so from here over to there, correspond to the working tape, and we need to track the movements of the head on the working tape as well. And the way that we do that is by keeping the head position as the central element. So we append symbols on either on the left and the right, depending on whether we move to the left or the right. So when you see a left or right movement, consider that as moving the entire tape instead of moving the head. And then over here, the second column from the right, they're the states of the pseudo-universal Turing machine itself, which I didn't actually introduce, so that's probably a bit of a confusing column. And the last one is just a time step counter for the pseudo-UTM. So if you take one of these random variables, say this Q here, then you're looking at all of the dependencies throughout the computation of the pseudo-UTM that lead to this particular random variable. And that's how we were thinking about this delta step t function. So there are a few simplifying assumptions here. You can look at the entire output of the step function, but that's a bit crazy. So we just look at the state. You can think about that as a Turing machine that accepts or rejects a string, for example. Okay, and then we define this posterior to be this delta step function, and we define this function h, which is some expected value, some sum of squares. Yeah, this model, sorry, and then this function here. And these are the geometric objects that we associate to a Turing machine. Okay, do I have that on the next slide? Yeah, I've got it here. So programs as singularities, programs here are Turing machines, and the singularities here are these pairs. So associated to a Turing machine M is the function germ m comma h, where bracket m means the code of m, and h is this function here.
Say what a classical solution.
A classical solution is when the true distribution is described by a Turing machine, so the function y here is computable, and then m is a Turing machine whose induced function agrees with that of the Turing machine corresponding to the true distribution. So that would not be probabilistic. Or I guess it could be. Sorry, delete that last sentence. Okay, so we described these. We described the geometry of this using the language of influence functions, which we define inside the paper. So these are just the partial derivatives of this model P that I had on the previous slide. Okay, and you can actually get some interesting behavior by just looking at the first derivatives. So when we are looking at an indexing corresponding to the standard basis vector, then we just write g sub I, where I is the position inside that standard basis vector, the position of the one, and then we write that instead of g sub I bold. Cool, so these functions are one of the central objects inside our paper as well. You've got this monster 90-page paper. This is hopefully saying, pay attention to these things if you're trying to read it. And this is one of the first lemmas that we had, where we can understand the partial derivatives of h in terms of expected values of these influence functions. Okay, so I've put the full definition on the slide, but just think about Cij as a constant. It's something that doesn't depend on the Turing machine itself, or it doesn't depend on the influence functions, and then you can see that the right-hand side is really determined by these functions Gi, Gj. Cool. So now we want to relate this to algorithmic structure, and, oh, sorry, there's a question here. Yeah.
W is the working state?
W is your description, so just,
It's a bit string.
yes, it's a bit string.
Derivative.
Ah. Yeah, the W1 up to the WD are the local coordinates of the space capital W, which is your manifold with corners, where points on it are these probabilistic Turing machines. These noisy Turing machines, I should be calling them. Right? And so you're taking a derivative of a function defined on a smooth manifold with corners. You do that by defining local coordinates and then taking normal partial derivatives.
The W is the coordinate of this problem.
Yes. So one coordinate Wi corresponds to a pair of bits inside your description tape where you take the difference of them. And you think about that as lowering the probability of reading one of those bits and increasing the probability of reading the other bit.
Epsilon is an example.
Epsilon?
You have epsilon going from zeros to the
Yeah.
epsilon of 1.
Okay. Very good. If I don't see your hand, please shout out, Will, I've got a question. Okay, so we mostly relied on intuition, but we can give some pretty concrete examples. Robustness to error would be one of them. So now we've kind of got a game that you can start playing, right? You have Turing machines on one hand, and you have these algebraic singularities on the other, and you can just go to town on that. You can say, okay, what feasible structure of the algorithm could I conceive of? And can I chase that through the mathematics and see if I can get some kind of visibility of that inside the function germ? We found a few such examples. One of them was robustness to error. Another one is control flow. So if you have a Turing machine that basically splits the inputs into two different types, and the first thing that the Turing machine does is works out whether you're of type A or type B, and then does process 1 if you're of type A and process 2 if you're on type B, then you can see that computational structure, that algorithmic structure, reflects structure inside the Hessian matrix of this function h, which I defined as part of the function germ. And I'll talk about that in a second. Okay, so to really nail down the algorithmic structure, we introduced this notion of error syndromes. And an error syndrome is a simple thing. As I was saying, the computation of this UTM goes back in history and takes a whole ton of samples on your square that you've done a perturbation on. When you do that, you can imagine getting most of those correct, maybe, and some of them incorrect. So some of those samples you get the incorrect reading, and some of them you get the correct reading. And then all of those different samples are going to be used at different points inside the computation. And a choice of those errors or non-errors is what we refer to as an error syndrome. So I drew this to give a bit more of a formal definition to what I just said. And also, again, I'm trying to help you read the paper, right? So formally, an error syndrome gamma is a sequence of functions, gamma 1 to gamma r. So imagine we have an algorithm with r inputs. And these functions map from a set containing ni elements into a set containing pi plus 1 elements. Think about ni as the number of times that that input is used. And then pi plus 1, so 0 up to pi, are all of the possible values that that input is capable of taking. And then the weight of the error syndromes is how many times you make an error for that particular input. Okay, so
Yeah, by algorithm with R inputs, you mean the specific algorithm state.
oh yes, I do.
Inputs of the description text.
Yeah. I confess this part is taken from the linear logic component of the paper, but yes. This is all fixed when you're looking at the specific example of the stage pseudo-universal Turing machine. Cool. Few questions. Yeah,
Do I just want you just go over that again? Just
for sure.
There's a lot going on there.
Yeah.
Yeah, there's a lot here. So the first dot point is the more important one. Do you remember the big, ugly graphical model that we had? Whole bunch of arrows. You can pick a particular node in that graph and then chase back all of the different paths from that node to the square where you introduced error. Say there are m such paths, right? Then it means that we use that square m different times in the computation of that node that I picked at the very start. So I've got m different usages of the exact same square on the description tape, and that square is possible of making errors, right? So I might have some of those m choices to be the correct one, and the others would be the incorrect one, and such a choice of correct, correct, incorrect, incorrect, correct for all m of those is what an error syndrome is.
When PI is 1.
Yeah, true. When pi is equal to 1. Yeah. And then to write that down formally, I don't like this slide anymore because it really depends on some linear logic. So maybe we can just focus on the first part. This is a pretty standard usage of the phrase error syndrome. Did I answer your question or not really? Do you want me to go through it again?
I think I understand. It does seems to me that in each of the usages you could have you could just have the transition, then in each place that it's used you could have the transition just sort of use more pointless. But I'll review this later.
Interesting.
I think I understand.
Yeah, okay. Sorry.
Is it correct, right, that this is the error here is this naive probability or combination, right, with error, so that every time I read one of these squares, I'm independently sampling from the distribution defined by that square. So you can also see it as this like long recursive process, or every time I read that square, I sample it.
Yeah, and then you track that history.
We can't hear any of that.
Yeah, okay. I don't know how to summarize your question.
Yeah, I was just confirming because it might be a bit abstract, sort of. I mean, the error syndrome requires talking about these paths, but the propagation of uncertainty you can see as just computation with error. Like every time I read from this square, there's some independent probability
Yeah, but it's more than that. So the question is, can we just think about this as every time I read from the square, I sample and possibly make an error?
I mean, that's equivalent, right, to the.
Nah. No.
Well, I swear we had this discussion. Okay.
It seems to me that it'd be equivalent from just having a probabilistic transition or every free square, but I'd have to actually.
Then you would have conditional. I mean, the squares would not be conditionally independent.
Yeah, but I guess what I'm saying is sample independently from this distribution, not. There's not one time you sample every time you.
Yeah, that's what I'm.
You sample. Are you guys saying every time my UTM reads this square, I sample, and whatever I get, I use what I got from that sample, and I carry on computing?
Yes.
That is not how this works.
No, yeah. You have to track every time you have the subsequent feed.
Yes.
Yeah.
You can have a single square on the UTM, which makes multiple usages of that one square with error inside it. Okay, that's possible. An example is on the working tape, you need to write down the new symbol and you also need to make a transition. Right? So when I'm working out what new symbol I write down, that depends on the description tape, which might be that square with the error. And then when I work out what direction I move in, that might depend on the exact same square. So I sample twice to work out a single movement of the working tape. Yeah?
Okay, so would this be a fair summary? Like in a normal probabilistic Turing machine, if you mess with like one square, it'll cause like a lot of correlation between the different branches. If it's 0 or 1 or something like that. But then in your model, you've essentially eliminated all sort of like correlation between like the subsequent random states. So like every state is independent, basically.
That's right.
Oh, okay, I see. So this actually confused me. Like earlier in the talk, you had this like space of states, but it was like the product of like distributions, and I was like, shouldn't it be the distribution of the products? But no, it actually should because it's all independent. Okay.
Yes, correct. Good work.
Yeah, okay.
Nice.
So if you do read the same input again, you don't resample, you use the same thing for the first time?
No, never reuse.
Never reuse like monotone.
And even two squares next to each other, like I think maybe in the model you have in mind, they could be like not independent, right?
Yeah, but they're independent.
Yeah, so like you sample from this one, it's like resample all the possible things that led to that in such a way that like reading from two tape squares will give you conditionally independent things. Like, I mean,
Okay,
condition on the original.
what does it mean to use input I and I times? So it's only used once? Or
I know that the updating of the working tape can use multiple usages of the same square.
So Will just gave an example where you need to use a square on the description tape to decide like which symbol to write and also which direction to move. Like, usually you would just like look at the description tape and then do the thing, right? But like you're using that twice and you need to resample.
yeah, and you always do that. So is NI always
At each subsequent step you're going to use it, you need to like resample as many times going backwards as you need to make all the things in the future conditionally independent. Like rows. It's a bit hard to describe.
Oh,
Yeah.
it's like you're keeping track of all the branches. So
Yes.
every time you've split in the past, like now you're
Yeah.
you don't like collapse the distribution like
No.
you normally would. Like probabilistic treatments.
Yeah.
So it is a concern that if you use the probabilistic Turing machine instead, then programs would not be singularities, or like you would not find structure as the geometry of singularity, or
I would say that it's just threat of the propagation of uncertainty not being interesting. Whether that would be geometrically uninteresting, but even computationally uninteresting. We want to have a strong distinction in our minds between the Turing machine itself and the induced function by the Turing machine. And then when we look at a probabilistic extension of the Turing machine, we don't want to accidentally slip and consider a probabilistic extension of the induced function of the Turing machine. Right?
So you could any probabilistic extension you choose will give some geometry. But like this geometry has you can write down the partial derivatives. There's like a very simple expression for it. So, I mean, I'm not, certainly there are other models, I mean, it's like an interesting thing to do to consider probabilistic ways of executing Turing machines and construct geometry. And nobody's saying this is like the only way that would be interesting.
So if we didn't follow the full construction, the point is that there's a construction that makes it differentiable.
Makes it differentiable such that the derivatives aren't just like some stupid junk that doesn't mean it.
Okay.
Which is like by default what you get if you try and
Go for it.
So is yet another formulation perhaps that it is a probabilistic Turing machine, but like the way you like measure the distance between two of them is like the single variable marginals at like a given point of the computation, essentially as a big vector, you know? That kind of
Saying like naive things, naive error propagation.
yeah. But then you just look at the single variable marginals, essentially, and then you're like, that's how I determine how close two randomized computations are, or something.
Not sure.
Okay, well,
I'm not sure.
yeah.
I do have more that I would like to say about this point, but let's leave it to after the talk. Okay. So to tie down the algorithmic structure, we spoke about these weighted error syndromes. So this is counting the number of weight S errors. Maybe I should go through this a bit more slowly. Okay, so if gamma is an error syndrome, then we define this thing just so that I can write down the following line in a simple way. So tau is some output of your program, and then S is one of these weights from the previous slide, which we've departed from now. Okay, so it's this vector down the bottom. Maybe I should have put that on the same slide here. Then these count the number of weight S error syndromes that produce tau, okay? And this object allows us to rewrite the expected value of the influence functions that I had earlier in the following way, okay? So this might look messy, but again, just in your mind, suppress the subscripts on the sigmas, so suppress the sums, and the C, ij, and the SS, and the ST. These are constants. The interesting part is when you blur your eyes and you see that the derivatives of H is equal or determined by the expected values of these sets that I just defined, okay? So this is the point where you should be looking at this and saying to yourself, wow, that is definitely geometric structure on the left and algorithmic structure on the right, giving formality and precision to our claim that such a thing should even exist. So to labor the point, the left-hand side are the partial derivatives of this function h, which we've associated to m, geometric. And on the right-hand side, it's this combinatorial thing where it's determined by the behavior of the of this flow of uncertainty. You can imagine where if your computation is robust to error, then this uncertainty would have less consequences moving forward inside the computation. And so that affects the right-hand side of this theorem. So as a concrete example of this, if you had a Turing machine that was robust to error of weight less than or equal to c for some fixed value c, meaning the following, then we have that all of these partial derivatives are equal to 0, and that's because the right-hand side of this equation is equal to 0.
Well, I don't think you've defined what curly U x gamma means.
Oh, sorry. Curly U x gamma. So curly U is the staged pseudo-universal Turing machine, okay? And then X is our input, so capital I is some finite subset of strings over the alphabet sigma, and then gamma is our error syndrome. So that is an input to the universal Turing machine, which is a noisy Turing machine. So it's the same when you run the noisy Turing machine on X, it doesn't matter that the Turing machine was noisy because that Turing machine is robust to error. Does that make sense? So you just get the outcome m of x. If that is the case, then these partial derivatives are equal to 0 as a corollary of our theorem. And then to those in the audience that know something about singular learning theory, you can take this even further and relate this to a associated local learning coefficient of the Turing machine. So this actually provides an upper bound. Very cool. Important slide. Any questions? We are getting to the end. Anyway, so control flow, this is the one that I was talking about earlier. This is also a nice one because you only need to consider the second partial order derivatives and the ugly coefficients in front of the expected values disappears. So this is quite nice. And you can see that the fact that the algorithm splits itself up in this way is reflected by the structure of the Hessian matrix, the appearance of those two zeros inside the matrix. Cool. Okay, that's essentially the end of the talk, and I just want to flag that this is truly only the tip of the iceberg. One of the most obvious questions that you can ask following our work is, can you reverse this arrow? So I want to repeat that what we have done so far is take algorithmic structure and then tell you how that is reflected inside the geometric structure. So that's an arrow from algebraic, sorry, I keep saying algebraic, from algorithmic structure to geometric structure. You can tell my training was in algebraic geometry, right? And then we want to reverse that arrow. So ideally, you're kind of doing computation via the geometry. If you want to understand the behavior of your program, you're doing that by looking at the geometry and then inferring back. Another question is, what other algorithmic structure has influence on the geometry of this algebraic singularity? So we gave two examples. There's a concrete example inside the paper as well, and you can just have fun thinking about as many different ones as you want. It's simple because we've got Turing machines in the picture, so you can think about it more cleanly than if you're using linear logic or something. Okay, can we implement similar techniques in other models of computation, for example, neural nets? That would also be a very interesting question. Great, thank you very much. That's the end of my talk, and I was mentioning at the very start that I got my hands on the drum kit. So there's going to be a musical performance later tonight and also tomorrow, and that's my music project. That's the other half of my life. I think this audience may be interested in it. If you are, by all means, chuck me a follow, get on the Discord. If it's not of interest, just ignore the slide. Thank you very much, and I'll open up for questions.
Can you just go back to the slide with the control example? Yeah.
Yeah.
Yeah, and just talk that through real quick why the hashing looks like that.
Because of... yeah. So did I say how we broke it up? Suppose I is I1, I2. Executes different things from the subset. Yeah, okay. We divide the tuples and thus the parameters into 3 blocks, where the first and second blocks correspond to the tuples in the first and second control path, and the third performs the classification of the input, right? So that is reflected inside the Hessian matrix, where row 3 and column 3, we don't know what they're doing because that's corresponding to the component of the algorithm which is determining whether you're in block 1 or block 2. And then the zeros are coming from the fact that you never end up doing anything inside. So if I were to make a perturbation in a part of the code which never is reached, then it's not going to make a difference. Does that make sense? You've basically you're taking the derivative in the direction of these tuples that are never reached by any of the inputs, because you classify first, so it's not inside that block.
Can you quickly remind me once again what the definition of W1 to WD are?
W1 up to WD are the local coordinates of the space W, okay? So W is this smooth manifold with corners where elements inside it are noisy Turing machines. That's a smooth manifold with corners. So if you want to talk about derivatives, one way of doing that is making a choice of local coordinates on that smooth manifold and then just composing through those local coordinates and considering derivatives from Euclidean space to Euclidean space.
So all the W is 0 just means all the entries on the description tape the machine M. And then increasing any of the W's is increasing the probability of reading the wrong bit on that tape script.
All right, so it's... We're sort of talking about here applying perturbation at different time steps at the UTM and how that impacts the output rather than
No, it's more like...
parts of the description code and how it's turning.
No, it's different parts of the description code. But like if you imagine if there's 2 sets of inputs, and on these inputs, some set of tuples are never used, then perturbing these will not cause errors on those inputs. And so perturbations that don't cause errors give you G's that are 0. So one of these G's is always 0. That's like in those spots.
So do we have some assumption here that in the description of the Turing machine, there's sort of a set of bits that says how to classify when I1 and a different set that says how to classify when I2? So like separate sets of bits?
That's just the bits in the third column. So then that's just like some other bits. So we're assuming there's a decomposition where some parts of the description do the classification and then pass control to some state like that is like for path 1 and path 2. And then those tuples for path 1 and path 2 are disjoint.
I'm going to talk to you afterwards, I still don't quite get it.
Okay. Yeah.
Any other questions? Although I think I've got maybe 1 minute or less even. Okay, everybody here should go to Billy's talk because he's going to run through some examples and then we can keep talking about it.
Thank you.
Thank you.